I think we have some time. I'll try to maybe speed it up a bit. I'm Lavrič. I'm coming from the Department of Catalysis and Chemical Reaction Engineering from the National Institute of Chemistry. And today I'll be talking about high-pressure stirred reactor system for high-throughput screening and optimization. In heterogeneous catalysis, for us researchers, it's really important to test large libraries of catalysts for certain in process conditions in terms of performance, such as activity, stability, and selectivity. And with this we speed up the innovation and development of such catalysts and processes. So today's topics will be, firstly, I will shortly describe this PAR 5000 reactor system, which is a high-throughput screening system for such reactions. And then I will go through two case studies from our laboratory, which were performed with this type of system. So first, a little bit of the history. I'm not selling you anything here, but PAR Instrument Company was actually established in 1899. And they were first founded to develop process, analysis equipment for coal. One of their first products was PAR calorimeter, which was used to determine the heat of combustion. This is still used today. Probably not this rusty one, but a new, more shiny one. But then later the company also focused on the design of high-pressure equipment, so reactors, stirred autoclaves, and also liquid autosamplers. As you can see here, this is one example of smaller reactors. Here we have also a scale-up for a half-liter reactor. And this is really nice liquid autosampler, which can be used for longer reactions, or if you have to sample tonight, you don't have to be there in the laboratory. And the company is headquartered in USA. So what about PAR 5000 reactor system? This is an integrated system which can run 6 reactions simultaneously at elevated pressure temperatures of up to 300 degrees Celsius and pressures of up to 200 bar absolute pressure. So we can run 6 reactions. We can adjust steering, temperature, and pressure. We have actually individual temperature control and pressure monitoring, and this makes it ideal for 3-phase reactions such as heterogeneous catalysis, which we perform daily on our department. So a little bit more. The mixing is ensured by magnetic stirrers. So first we use, before we mount the head on the cylinder, we can choose from these different magnetic stir bars, depends on our application and reaction media. Then we can start the reaction, let's say, with this nice graphical user interface, where we can monitor a lot of parameters such as temperature, pressure, the change of pressure through time, and we also can see if there was any alarms of the reactions escaped or anything like this. So it has a really easy control of the system. And this is the actual reactor in the laboratory. So we can see here we have this tube is actually to fill in the gases in the headspace. Then we have here, it's a 3-way valve and a needle valve, and this is a deep tube, so it allows us sampling through time the liquid reaction media. By default, this system, when you buy it, you get stainless steel cylinders and heads, but if harsher reaction conditions, such as low pH, is required, also there's a Hastelloy variant of this reactor. So what can you actually do with these reactions? Well, let's check out these 2 stories from our lab. So in a broader sense, this is a reaction from how to get from biomass to nylon 6,6, and these are all the important intermediates in between. So from glucose, we perform oxidation to get glucaric acid. And then we perform dehydroxylation and hydrogenation to obtain adipic acid, which is one of the monomers. So let's first dive into the oxidation reaction. Glucaric acid in 2004 was classified as a building block chemical with many potential by US Department of Energy. This is the molecule. It can be also a lactone or dilactone. And these potential uses are, it can be used as a retardant in textile dyeing, also as a chelating agent in detergents and surfactants, There are some studies that it can be used also as a beta-glucuronidase inhibitor for cancer prevention. And the most interesting for us, obviously, is the precursor for the bio-based adipic acid production. Current industrial norm for this process is the oxidation with nitric acid. It's a really old process, and it produces a lot of NOx harmful emissions. We have to deal with the nitric acid discharge. And also the reaction is really exothermic, so we have to operate at low temperature, at low yields, because there are some safety risks. Also, I want to show you this. So this is the compound annual growth rate for the glucaric acid, and you can see that it's around 10%. So in the following years, it will soon reach 2 billion. And most of all, and the highest, so the demand is increasing, and the most of all, it's increasing for pure glucaric acid. So what was our motivation in our investigation? Well, there have been a lot of studies with monometallic gold or platinum catalysts under pH control conditions, but only for the first step from glucose to gluconic acid, while there were far less studies to go down to glucaric acid. And also there was really only 2 or 3 mechanistic studies where they modeled or tried to model the entire reaction pathway. So we decided that we're going to try to get some sense of the difference between monometallic gold, gold platinum, and gold copper catalysts. They were chosen because gold is stable, but really not reactive because you need base. Platinum is more reactive, but it leaches from the it leaches through time, and copper as an alternative to expensive platinum material. So they were supported on zirconia dioxide because in previous studies, when they tested different supports for similar nanoparticles, zirconia dioxide was obviously the best. So we used that one. The catalyst synthesis is described in the paper, so I will not go into details here. We performed some material characterization, XRD, TEM, and oxygen chemisorption. And also we performed a microkinetic study, which was compared then also to a DFT study, so density functional theory. So let's just skim through the findings of the characterization. With XRD, as you can see here, for pure gold, we have this Bragg reflection for 111 gold plane, which is not present here in the bimetallic catalyst. So either we formed an alloy or the particles are too small for the detection limit of XRD. And we also did not observe any other peaks for pure platinum or pure copper. So this is one indication that perhaps we formed an alloy. We also did high resolution TEM, and from the lattice parameters, we observed that for the gold-platinum combination, the lattice parameters were 2.5% smaller, which is in accordance with Wegeard's law for 50-50 alloy composition of gold and platinum. We also observed that for gold-copper, the particle size distribution was less homogeneous than for gold-platinum, and we also performed SAED diffractions, and we observed that for gold, we have a nice match between the simulation and the actual sample. So these rings, which represent the planes, were aligned. While for the bimetallics, these experimentally observed rings did not match to either gold or platinum, but were somewhere in between. So this is another indication that we formed an alloy. We also performed the oxygen chemisorption because we need oxygen on the surface to perform this reaction. And we saw that the bimetallics actually absorbed 2 times more of oxygen, with platinum being the best among the bimetallics. So then we performed a number of experiments with the mentioned catalyst, the reaction system. Around 37, we determined more than 250 experimentally determined points for all the intermediates and products and reactants. And we tested it at various temperatures, pressures, and then we used all of this data, tried to perform a regression with the model that we envisaged with this reaction pathway. And then we obtained the reaction rate constants and corresponding activation energies for each reaction step. At the beginning, we also tested the blank reactions without any catalyst, just to see that there is no competing reaction in the bulk liquid phase, which was obviously not. So what was the basic idea here? So as I said before, we performed the reactions, feed the model with the data, perform the regression, and obtain these nice plots. So as you can see, the best results were obtained at higher oxygen pressure. And as you can see for gold, there is practically no glucaric acid. We formed some gluconic acid, but we saw some glucaric acid, but only in traces. And also we saw that the carbon balance really dropped through time. So we probably formed carbon dioxide at the end of the whole reaction pathway. With gold copper, the results were more promising. We saw more glucaric acid, but at the end, the yield was really much more lower compared to gold platinum, which basically gave us at the best conditions, which were 100 degrees Celsius and 30 bar, gave us around 30% yield at these process conditions. So the concentration and the ratio between the catalyst and so on. Then we reversed the model and then tried to make it like, now you tell me which is the best time and temperature for this reaction. And we got this nice surface plot. And we observed that the reaction time should not be longer than 200 minutes because then you lose the glucaric acid. But also the temperature should be in the range from 100 to 115 degrees Celsius to obtain the best yields. We also performed DFT study. I will not go into really great details here because there's a lot less time, but we observed basically that gold absorbs molecular oxygen mostly. Platinum absorbs molecular oxygen, and also it performs decision to atomeric oxygen. And copper really produces only atomeric oxygen, so it really activates it from the molecule to the atoms. So we observed, these are the calculations were made for pure metals, not for the bimetallics. So we cannot really directly compare them with the macrokinetic model, but like indirectly it can be. So we saw that platinum was actually the most suitable with all this activation energy that we observed here. But it was problematic because it actually favored the cleavage to lower C carbon products. So basically alloying it with gold enhances the selectivity and catalyst stability. And we also, where the models correspond, was the oxidation from gluconic to glucuronic acid. So this is the rate limiting step. And with DFT, we saw that the activation energy was the highest. And also here we saw that these reaction rate constants for the second step are much more lower than for the third and the first one. So this is a brief description of the experiments and the study. And in greater details, you can find this through this QR code to check the paper. So the next step was actually from glucaric to adipic acid. So here we have a different kind of reaction. It's a dehydroxylation and then later hydrogenation reaction. And this was actually done by my colleague Brigitta. So the background here was that rhenium oxides and these complexes are really good for this reaction in a homogeneous type of catalysis. But the problem there was that each cycle it's hard to remove the actual catalyst from the reaction mixture after the reaction, and also we basically lose catalyst each cycle, so it's not cheap. So Brigitta's tasks were to try to develop the heterogeneous catalyst for this reaction, which could be reused many times. And as you can see, here is the reaction pathway. So first of all, we start with this one. We need to first cleave off these hydroxyl groups from the molecule to obtain these double bonds. Then these double bonds are saturated with hydrogen to obtain this dimethyl adipate ester. So what were the findings? Well, under the hydrogen atmosphere, we first tested the different supporting materials, so silica and alumina and carbon, and we saw that with these two, there was practically, the yields were negligible. But with carbon, we obtained around 60% overall yield for all the for all the intermediates and the final product, we saw that if we increase the temperature for 20 degrees Celsius, the overall yield is not increased, but selectivity is improved. So this means that the dehydroxylation is not faster at faster temperatures, but hydrogenation is. We also observed that if the catalyst is dried, the yield is substantially increased, and similar with the reduction in the hydrogen atmosphere, the yield is again substantially increased, and also the selectivity for methyl adipate is slightly increased compared to this one. So, in order to improve the selectivity towards our final product, not these partially saturated products, we can also use co-catalysts such as palladium on carbon or platinum on carbon. And it turned out that palladium on carbon was the best catalyst for this reaction, forming around 60% of the dimethyl adipate. So she also tested the same reaction under inert atmosphere. And we observed that at lower temperature, we formed basically this dehydroxylated product. If we increase the temperature to 175 degrees, we don't improve the overall yield, but we improve the selectivity towards partially hydrogenated products. If the catalyst is reduced, the yield is significantly improved. And also, if the reaction time at the lowest temperature is increased, so you can see here it's a really long reaction time, is increased, also the selectivity is improved, and this is similar to if we increase the temperature, we obtain much more methyl adipate. So one would also ask, where did you get hydrogen from in these conditions, right? Well, here, because we are using methanol as a solvent, methanol is actually oxidized and forms hydrogen, and we also observed hydrogen in the gas phase of the reactor when we sampled it. So what are the benefits of this second process? Well, we have relatively high yields. We don't have any gas emissions, no harmful side products. It's a heterogeneous catalysis, which means that we can easily separate the catalyst by filtration. We can reuse the catalyst because we can reduce it. We can reduce the catalyst and use it again, and we can also reuse the solvent because we can just distill the methanol out. And it shows that the transition to a continuous process here is also feasible. So at the end, I would like to give a big thanks also to SRIP for providing us with this PAR 5000 reactor series. I would also like to emphasize that all SRIP members are invited to perform experiments at our facility with the help of our operators and a lot of ready-to-use analysis equipment, as you can see, HPLCs, GCMS, TGA, etc. And we are always open for collaboration. And also, at the very end, I would like to thank my department, all the colleagues. We have a really nice chemistry over there, so you can visit our website, follow us on Twitter or X, and you can send me an email. Thank you.
Thank you very much. Maybe really just one quick question, because you deserve it, according to the work done. Are you thinking about scale up, or this is like really for the catalyst?
Yeah, we are thinking about the scale up. We also have the equipment. So we have, as I showed you before, the half-liter reactor. We also have a 10-liter reactor. But maybe the scale up is more, how can I say this? The second reaction step, right, has higher yields. So the scale up there is more feasible, while in the first step, we need to maybe test some more different conditions to make a better kinetic model, which can predict the higher yield of nucleic acid at the end, just for the process to be economical.
Okay. Thank you very much.